Okay, welcome to City College of San Francisco Engineering 20 final review session given by me, Wendy Kaufman. And I just want to remind everybody again that City College is open and accredited now throughout the end of the year and most likely forever, because we are a wonderful school and we are gaining in our struggle for accreditation. Okay, so I had a couple of requests, nothing specific, so I hope what I chose is going to meet the needs of the people that actually did do some requests. So someone asked me for a first order circuit with a switch, someone else asked me for an op-amp, and then someone else said I want a more complicated problem, so I think I've got it here. It's a first order circuit, and we know that because there's just one energy storage element. It has an op-amp in it, and it has a switch. So I think this meets the requirements of a complicated problem. We are asked to find the output voltage at the op-amp for all time after t equals 0. So we're looking for a function of time for that output voltage at the output of the op-amp. Okay, let me just talk just for a sec about op-amps in general. I know that sometimes students feel intimidated by these things, but just don't. They're only models, like everything, like a resistor is a model. Capacitors, they're mathematical models of what happens, in the real elements in a circuit. So, like for instance, the model for the resistor is that the voltage across the resistor is always equal to the current times the resistance of the resistor. And we know that the directions are important. But, so for the case of the op-amp, here's the model. We only treat it as a 3-terminal device. It's actually got a lot more, which we do have to take into account. But for the most part, in our problems, we can just show it as a 3-terminal device that has an output voltage. So this node here, if this is the reference, I could label this node as V0, because it is the output with respect to the ground. And then we've got a voltage at the inverting node and the non-inverting node. Okay, so if I call the one at the non-inverting node V1 and at the inverting node V2, and then there's also going to be some currents here, which I'll label I2 going into the inverting node and I1 going into the non-inverting node, and then there's also a current here that I'll label I0, which is at the output. Okay, here's the model of the op-amp. If it's ideal, then V1 is equal to V2, and I1 and I2 are both 0. So this is the model. For an ideal op-amp, the voltages at the input nodes are the same, and the currents are 0. That's it. If you just use that model, then you're fine. Now, the thing you have to be a little bit careful of is when you have a problem with an op-amp in it, usually the best way to go is node voltage analysis, but you have to remember 2 things about applying node voltage analysis, and that is you cannot do a Kirchhoff's current law at the ground or for the op-amp itself. And that has to do with those, I mentioned that it was actually more than a 3-terminal device. And so there's actually some power lines going into the op-amp into the ground that we're not showing. And because of those, that's why you're not allowed to do Kirchhoff's current law at the ground node or like considering the op-amp itself as a node. So if you just remember those 2 things and the model for the op-amp, then op-amps shouldn't be an intimidating thing in a problem. You shouldn't be afraid of them. And we're not afraid. We're not afraid of op-amps. We're not afraid of the ACCJC. We are just not afraid. Okay, so getting back to the original problem, I'm just going to erase this stuff that we don't really need in the original problem. We've got this circuit, we've got a switch, we've got a capacitor, we've got an op-amp. We're asked to find the voltage for all time after t. So the first thing I want to do is acknowledge that this is a first order circuit. And so because it's a first order circuit, I know how to handle this. I know that if I can just get the Thevenin equivalent from the perspective of this energy storage element, in this case the capacitor, then I can just apply my formulas. And so that's the direction I'm going to go. Before I do that though, because I know in that formula I'm going to need the initial voltage across the capacitor at t equals 0, so I'm going to just do a little bit of work before I do that Thevenin equivalent. I'm going to consider the circuit at t less than 0. Okay, so before this switch opens, see how the switch is? It's going to be closed, and then at t equals 0 it opens. That's like the meaning of this arrow right here. It opens when t equals 0. So that means it's closed before t equals 0. So if it's closed before t equals 0, look at it. This, as closed, is in parallel with this resistor. That makes that resistor a short. So I've redrawn this circuit with this resistor shorted out. I didn't show the open switch because I kind of ran out of room, but why show an open switch? It's just open. It's not going to affect anything. And then we have this capacitor. And the idea here is that if the circuit's been like this for a long time, then this capacitor is acting like an open circuit, right, for a DC voltage. So this is like an open circuit. I don't even really have to show the capacitor because this is just acting as an open circuit, so I'm just going to open it up. But I'm still going to show that voltage because that voltage across the capacitor is still the voltage across these two nodes here. And that's the open circuit voltage. Oh, you know, I'm getting into another part of the problem I didn't mean to. So all I need to say here is, look, what's the voltage across that capacitor? It's 0. Okay? So for the circuit at less than, when the time is less than 0, you know, in other words, before that switch opens up, the voltage across the capacitor is 0. And then, because we know that a voltage across a capacitor cannot change instantaneously, now I've got my initial condition for the voltage across the capacitor for all time greater than 0. Okay, so I'm going to erase this now and just keep the conclusion, which is the idea that the voltage, maybe I'll just, I don't know, I'll put it as a, I'll just put it here, that, you know, we did some work. You wouldn't have to erase on your paper, of course, because you've got more paper, but I don't have more blackboard. So this is the important conclusion here, that the voltage at t right after 0 is 0 volts. I'm going to need this when I start plugging into my formulas for a first order circuit. All right, in other words, it's that x0 from the previous videos. In this case, we're looking for the voltage, so x is V, and then the initial voltage is, we called it x0. So in the formula, that's what it is that I'm going to plug this into. All right, so now I'm going to go and do the work of finding the Thevenin equivalent for this circuit from the perspective of the energy storage element. Okay, so, and of course that's when t is greater than 0, because that's what I'm looking for, is the voltage, well, yeah, the voltage after the switch opens. By the way, this is asking for the output. I'll show you how it relates to the capacitor voltage in just a second, and it does. So, so the picture then, after the switch opens, looks like this. You know, this before the switch opens, and this is the same picture, really. Oops, I didn't label this here. 20 kiloohms. The only difference now is I'm not showing the switch. That's it, the only difference. Not showing the switch. And also I've labeled, instead of labeling this voltage here V0, I just labeled the node voltage V0. So what I'm going to do now is what you do for any first order circuit. You find the Thevenin equivalent from the perspective of the energy storage element. So from the perspective of the terminals A and B, I need to find the Thevenin equivalent. So in other words, I'll draw it like this, A and B. The Thevenin equivalent is going to be some resistor in series with a voltage source. The voltage of the voltage source will be the open circuit voltage. The Thevenin resistance will be the open circuit voltage over the short circuit current. And once I find these two values, then I've got the Thevenin equivalent at AB. I put the capacitor back. I've got a standard first order circuit, and I can just plug into the formulas. So we'll do that in the next segment.